officer and professor, respectively, from 2001 to 2015. He received a PhD from Kyoto University in 2000 and a second PhD from the University of Ottawa in 2007. His research interests include predictive maintenance, infrastructure condition assessment, machine and computer vision, data analytics, sensor and measurement systems, non-destructive evaluation, and digital twin. Professor Liu is a fellow of SPIE and the Engineering Institute of Canada. He has professional engineering licenses in both Ontario and British Columbia. Today, Professor Liu will give a presentation titled Digital Transformation of Infrastructure Condition Assessment, Case Studies from the Oil and Gas Sector. Please join me in welcome Professor Zheng Liu for his great presentation.
Thank you for Dr. Li's introduction. Good morning, everyone. It's my pleasure to have this opportunity to give this seminar on the digital transformation of infrastructure condition assessment. So especially today, I give you some case study of the oil and gas sector. So yeah, this is my presentation. Let me see here. Okay, it's fine. Okay, so this is the agenda. So first I give you a brief introduction about the university and myself, and give some background information about this work. So, and I want to describe the challenge for condition assessment, and I give you 3 case studies for the oil and the gas industry. So then I share the lesson I learned from this work, and finally summarize this presentation. Okay. So myself, I think Dr. Li already introduced me. I was educated in China, Japan, and Canada, and now I'm leading the intelligent sensing, diagnostic, and prognostic research lab. So basically, I would say acquire information and processing information. Okay, so I worked before in Singapore, Canada, and Japan, and now in UBC, Okanagan. So this is for UBC, we have 2 campuses. So the main campus is in Vancouver. You may already know that. So another campus is in Kelowna, which is about 1 hour flight from Vancouver. So this is in Okanagan region. So if you drive, it's about 4.5 hours from Kelowna to Vancouver. So our campus is relatively young. It's about 20 years old, but it's a fast-growing campus. Okay. So now we have 12,000 students, including 10,000 undergraduate and 2,000 graduate. And we have this these numbers, let's say research funding, it's grows rapidly, and other programs, any programs available. So by the way, Kelowna, that is a beautiful place, especially summer and winter. For winter, we have the ski resort, and in summer, we have the golf, and we have a lot of orchard and vineyard there. So the best wine come from this area. So this is the weather condition somewhat like Xinjiang in China. Okay, so we have a lot of fruits in this region. Okay, so then about the Canada pipelines. So you first look at the map on the right side. So basically, this is the the pipeline across the Canada. So from west coast to east coast, because the Alberta is the center of the oil production in Canada. So, but the oil transport from west coast to east, we have to go to U.S. first, then U.S. back to the east part of Canada. So that's the issue. And recently, I think the government built another pipeline from Alberta to like west coast, like Vancouver, this area, because Canadian government looking for the business opportunity in Asia Pacific market. So this is a newly built pipeline, and previously it was owned by a company called Trans Mountain Canada. So finally, the government acquired the business because there's a lot of issue when you build this pipeline. It's go across the indigenous people's land, a lot of issue, environmental politics. So the government take over this business. I think it's almost done, as claimed in the news. Okay. So basically, for the pipeline, we have three types of pipeline: gathering pipeline, feeder pipeline, and transmission pipeline. Okay, so this pipeline transport the oil product to the end user. You go to the gas station, take your gas for your vehicle. So that is the transmission and even distribution facilities or even pipelines. I think usually you use a truck, right? You see the truck, go to the gas station and fill the gas station, you can use that. So this is the type of pipeline we have. So again, this is another figure show the number of the pipeline length in pipeline infrastructure in Canada. Okay, so we have a different type of pipelines. That's a gathering pipeline, feeder pipeline, and transmission pipeline and distribution pipeline. Okay, different pipeline. So for pipeline, we have a different regulators. Let's say federal regulators, provincial regulators. You want to build a pipeline from Canada to US, there's a regulator in the US. The two different regulations should be matched to each other. So yeah, there are a lot of regulation issue because any failure of the pipeline will bring the severe consequence to the environment and the people. So basically, the pipeline integrity management, we call PNM, that is the core for the pipeline industry. This is very important. So there are four components in it: plan, do, check, and act, right? So this is basically in a pipeline integrity management program. So any regulator comes to your pipeline operation, they say, do you have this pipeline integrity management program or not? They're looking at how you manage your pipeline, right? Manage your pipeline. So this is basically what people use for pipeline management. So for condition assessment, what will be the challenge currently we have? So we do the inspection, but this is a periodic inspection, right? They have the they use the inspection services from the company like GE, like Rosen. So they do the pipeline inspection periodically and give you the report. So, and also the inspection, they use a single sensor system, and they need the people to interpret the inspection results. So then you make the decision, say, okay, what happens, what we should do for that. That is the how you do the maintenance. And the information, that is a lot of silos with information not being shared with a different sector department. Okay. But at the same time, we have the challenge, let's say aging infrastructure. It's been getting old, okay? And the consequence of the failure. So it's very costly, right? And brings the damage to the people and the environment. And also we have the need for the technology, advanced in technology and smart city development. So therefore, the conventional approach do not meet the current need and demands for the safety, reliability, and efficiency requirement for the this oil and gas sector. So digital transformation, that is essential. Okay. So then I talk about to give you 3 case studies. So if you have any question, just stop me. I can discuss. So the first case study is multi-sensor ILI inline inspection data fusion. So this work is with Rosen Group. So Rosen Group is a company headquartered in Stans. So that is German business. It's a big global company. So they do a lot of pipeline inspection services across the different countries. So I think they have more than 3,000 engineer for the R&D. They have the most advanced hardware for they call the peak system for the pipeline inspection. So the bottom figure show the head square stand. In that stand is in Swiss, and the other one is their office in Kelowna. So they have a data group currently located in Kelowna, okay, in Canada. So they also have a branch called Rosen Technology Canada, okay. So they do their that's in Calgary. So they do the services for the pipeline inspection, and their data group in Kelowna, in the city in the city we have. So for Rosen, they have different tools. Let's say they call peak system. They have the magnetic flux leakage. So this is one of the most popular non-destructive inspection technologies. Magnetic flux leakage, they have a different configuration. One is the actual. So based on the sensor, how you configure the sensor, one is called actual magnetic flux leakage. The other is called the circumferential magnetic flux leakage. And they also have the ultrasonic wall measurement and crack detection. And also with the electromagnetic acoustic transducer. So this is the different tools they have. So keep in mind, when we use the ultrasonic tool, we need the media. So let's say you do the B scan at the clinic. So they should apply some gel on your body. So then the sensor move on your body to the inspection. So therefore, the UT inspection must have some media, like a water or something like that. So usually that will not be used for the oil and gas pipeline, gas pipeline used for the oil pipeline, right? So when you do the inspection, you can select which one you use. If you select multi-models, you need to pay more because let's say the price depends on the length and the model you selected. You select multiple models, so you pay more for the services, right? But looking at the advantage, they have different, let's say MFLA with at the pitting and the general circumferential anomalies. Well, the circumferential MFL good at the actual anomalies, right? The different methodology have a different features. So basically, here is the procedure when people do the analysis. So they do the inline inspection with the peak system, got the signal, and using a sizing model. So the sizing model is proprietary solution from the industry. So that is from the signal, they can generate the size of the corrosion damage. So the size they give you like a bounding box, right? Like a bounding box, square, rectangular bounding box. So then they have the bounding box give the information about the area, depths of the corrosion. Okay, so this is called the box data we have. So with the box data, people can do the make the decision. So whether we should just monitoring or need to repair or do the on-site inspection, because the on-site inspection like a digging, right? You're dig out the pipeline and do the on-site non-destructive inspection. That will be very costly, very expensive. And the other thing, we have the box data. So when people compare, let's say they did the inspection on year 2000, and 5 years later, year 2005, they do another inspection. They got the boxing data from year 2000 and 2005. They want to calculate the corrosion growth rates. So in that case, they need to do the matching of the boxing data, right? Because they say, okay, this is the same location associated with the same pipeline, pipe segments. That's the most important, right? Most important. So there's a need to do the alignment for the boxing data. Okay. So basically, we come up with some idea. So multi-modal fusion. So what do we do? Let's say we have this is flow chart. We have the different, let's say MFLA and MFLC, the different model. Then we collect the data, looking at the historical data with the like machine learning model. We understand the performance or the probability, reliability information. Then we can do the matching for the data alignment, like the boxing data. So after the alignment, we can do the data fusion and integration. Then we can go to the decision making, because we think this fusion process can give you more accurate measurement of the corrosion damage. So basically, because you know the machine learning or whatever, we need a ground truth data. So the ground truth data come from the the laser scan. So you're like we do the laser scan, get the accurate corrosion damage. Then we use that data for the modeling. Okay, for the modeling process. Okay, so one approach for the box data alignment. So this is done one of my PhD students. He actually proposed a solution process, let's say pre-processing, grouping, do some alignment and matching, and got the aligned boxing data. So, but here, yeah, we have this publication. You can look at the details about the detailed procedure. For the boxing data, there's an issue because when you're sizing the damage, so there are errors associated with the process. So when you do the alignment, they will introduce another uncertainty and errors, right? So that could be the issue for that. And the boxing data, again, this is not we will not say it's not accurate, but this is just a representation of your damage. But the damage is not always like the boxing, like the rectangular, right? They have different shape, different combination. So there's some information missing. So therefore, we're looking at the original inspection data. For example, we have the magnetic flux gauge data on the left side. The other side is ultrasonic measurements. So this is the two kind of measurement. So when we want to do the fusion, again, we need to do the alignment. Okay, alignment this data, let's say associate with the same pipeline, right? So, but this is the data of different format because of the physical principle behind these two inspection are different. So what we can do? So we come up an idea, let's say from the image translation. For example, on the right side, you see two different images. So one is just a horse, the other is a zebra, right? So this is we can transfer the translate the image on the left side to another, different style. Like, so therefore, idea is whether we can translate the one like a MFL image to the UT image, then we do the alignment. So this alignment in image processing is called the registration. For example, you see the bottom, that is the remote sensing images. People do the registration. Usually we can do the scaling, rotation, and the translation. So that is the image registration. So basically, we come up with the solution. First, do the translation. Here, we did not do any new invention for the methodology. We look at the current solution, which is best for our application. We also look at which direction. Let's say we can translate the UT image to MFL. We can also translate MFL to UT, but which direction is better, right? So we do some experiment. We identified we should translate UT to MFL. So after the translation, so we come up with a solution, let's say using the a matrix to do the registration. So make sure each pixel, the 2 pixels from the 2 different images, associate with the same physical point on the pipeline. So this is the idea. So here is an example. This is on the left side, this is measured MFL, measured UT. So the MFL can use different approach, translate to the UT. Okay, so you see which one is the best, then we use the best one to do the registration with UT. Okay, so before this is not possible because they don't share some common features. They don't share common features. Therefore, we do the translation first. So the other one is we can also translate the UT to the MFL. For example, this is the top is UT, translate to MFL, and this is the true MFL. Then we use the MFL to do the registration with the translated UT. But here there's some issues with that, because when you build the translation model, there's different ways. Let's say you have paired image, you build the model. You don't have the paired image, you build the model. So which one you can do, right? So that is a lot of different setup and background information. So you can check our publication for that. So here is, let's say, you see the different modalities. Let's say you have the MFL, you have the UT, and that is the ground truth. The ground truth being obtained with the laser scan, and you see the advantages of the 2 modality, right? So sometimes, let's say UT gave the better results. Sometimes the MFL gave the better results. So therefore, we see the benefits for fusing these 2 data together for the corrosion characterization. Okay, so therefore, this is another student of mine. She proposed a solution and do the fusion. Okay, do the fusion. So basically, this paper has not been published yet, but she just read it in her thesis. Should be available soon. Okay. So here's some number associated with this experiment, and also here is the matrix she employed. So for the fusion, usually we use the mean square error, right? But that is not enough, because we also look at the depths, the peak depths of the corrosion, corroded area, because that is critical for the risk analysis of the pipeline operation. So therefore, we consider different metrics to evaluate the fusion results. At the same time, I think that the also here is the another interesting thing we did is we also quantify the uncertainty associated with the fusion result. So that is important. why uncertainty is important, because that helps with the decision making. So let's say you can give a estimation of the depth, a single value, but that value, the engineer, they don't know how to use that. But if you can give a interval, let's say could be the maximum depth, this could be the minimum depth, and they have 90% of the chance to fall in this range. So when I do the risk analysis, I consider the worst scenario. I use the maximum value, right? Not the single value plug into that. So that is interesting. And also we have the individual technique, let's say UT-MFL, and we have the fused method. So looking at the uncertainty, so the fusion method gives you a narrow interval of the results, which means the uncertainty has been reduced. But this is just a start. Again, this is still from the modeling perspective. So let's say if you change your model method, if you change your data set, so this number might disappear, might change. So I'm still looking for some uncertainty associated with the technology. So that is a lot of things. This is just start. A lot of things need to be done in this area, right? But it's interesting. Okay, so here we talk about the uncertainty. We have some considerations about this research. Like other data or modeling work, when you have different data set, let's say for the training, the performance may change. That create a problem for this industry. Let's say you have this specific data set, build your model have a performance. When you have different data set, you have different performance. When you use different data set for testing, you have different performance. So that could be the issue, right? How we can solve this problem. The other is, will the fusion always give you the better results? The answer is no, because I think we already studied that. Depends on the size, depends on the type of the corrosion. So sometimes the UT gives the better results. Sometimes MFL gives the better results, but sometimes the fusion gives you the better results. So that is a very important, critical information. And because when you mix all the data together, you finally generate a number for the metric. You always get good results. So that may confusing, right? So be careful. I think we should. This is another area we should be further explored. Okay, and the other issue is for non-destructive testing or evaluation, probability of detection. That is a key information with a NDT or non-destructive testing system. So when you introduce a model, whatever, machine learning, AI, or deep learning, okay, so the probability of detection, this information is missing when you have looking at the whole system. So that could be an issue, because that is really depends on the data you use to build the model and the data you use to test that. So without that information, probability of detection, so that created the difficulty challenge for the decision making, right? So probability of detection and uncertainty. So these two information, that is critical for the pipeline integrity management system. Okay, so how we can have the probability of detection? That is the interesting topic. I keep thinking how we can, when you have a deep learning model, how we can get that information, right? Okay, so this is the first case study. So the second one, we built a pipeline digital twin. So this is a project, 3+2 project with the Canada and Germany. So Canada, we have 3 organizations: National Research Council of Canada, UBC, and a company called Verum. And in Germany, we have another partner. One is the Fraunhofer, the IKTS Institute. Fraunhofer, like the research institute, like a Research Council of Canada. This is a national institute. They serve the small business in Germany. IKTS is a ceramic technology institute. Okay, so they have a strong expertise in non-destructive inspection. And we have another partner, industry partner from Germany. So that company is working on the bridge maintenance, bridge inspection. So here in this study, one work is about the pipeline, the other work about bridge. But today I only talk about the pipeline. So the Fraunhofer, they developed the acoustic sensor ring. Okay, so we use the acoustic sensor ring to do two things. One is crack growth prediction. The other is corrosion damage characterization. So there are two different type of damages here. So the figure on the right side show the crack growth experiment. So they have the crack, they apply the cycle to the pipeline and make the crack growth. Then they have the acoustic sensor ring capture the acoustic signal. Then we do the prediction based on the measurement and online monitoring. Okay, so basically here is a model. Again, this is done by another PhD student of mine. So his thesis is available online. So basically he has different models for that. The core solution is a Bayesian inference and phase-based model, surrogate model. So they do the crack growth prediction. So actually I'm not very happy with the flow chart. He have this. I think it could be even clear. But anyway, so you can find his thesis online. It is available. Okay, PDF version of this. He did a good job anyway. So there's a different models associated with this framework, computational model, signal processing, finite element, data-driven, and other mixed model, Bayesian model for this. So this is basically a combination of physics model and the data-driven model for the prediction. But at the same time, we do the online monitoring and do the offline inspection. So let's say after 100 cycles, or 200 cycles, we do the manual inspection. So manual inspection, let's say we use just a ruler as a measurement, measure the crack size, using that information as an input. So then that input can further update the model. When they go to another cycle, so the model getting more accurate. So otherwise, you have the error from the beginning, the model keep running, it's getting the deviation, the error getting larger. So the offline inspection help with the correction of the model. Okay, I think that is very useful information. That also makes sense because you do the annual inspection or you have the maintenance time, you can have that information, right? So that's possible. So basically, we work with the company in Verum. So they have a web-based digital twin platform. So we can build a nice-looking 3D model of our pipeline on their platform. Backbone is AWS from Amazon. So and also we can use the Microsoft HoloLens. They can build small tools. You can human like a user interface can interact with this 3D visualization for that. Okay. So and second part, we look at the corrosion. So corrosion is another experiment. So they introduce the corrosion damage to the pipeline and accelerate this process. So come up with some chemical solution attached to the pipeline and generate the corroded area. That process is really time consuming. So we look at two things. First thing, we want to measure the thickness of the pipeline. This is first thing. So basically, we look at the 4 different model and we identify, okay, the LSTM can give you the best solution for the estimation. So this is just we're looking at the two boxes and pick up a tool and do the work. So the other work is we have the sensor ring, right? Sensor ring, we call the sensor acoustic sensor data. We want to reconstruct the corroded area. Okay, corroded area. So that's a different reconstruction solution, and we come up with our solution. It's called RAPID. So we got the reconstructed results, which give the best performance. So this paper published on the IEEE transaction, you can find that. So from this study, so again, some lessons I learned. So the role of the acoustic sensor. Okay, so acoustic sensor that can be applied to the pipeline. But let's say if you have pipeline of 10,000 kilometers, so the acoustic sensor can only monitor a specific segment of the pipeline, cannot be applied along all the pipeline, right? So let's say you have any repair, you have any critical parts, you want to do the monitoring, acoustic sensor is the solution. Not say you should apply the acoustic sensor along all the pipeline. That is not possible. Okay, so the other one at that time, we're looking for digital twin. So what we did, so we have a 3D model. We can do the real-time data mapping. Is it called a digital twin? We can do the prediction. Is it a digital twin or not? So I would say right now, I think I would say it is 80% or 70%. It is digital twin. It's not a true digital twin. So what is a digital twin? It is. So this is the flow chart I have, but this is maybe take another 1 hour to explain what is the digital twin it is. Right now, people have a different definition or different presentation about digital twin. So everything is a digital twin. So it's cheaper, it's popular, it's everywhere, but there's no commonly accepted definition for that. So I'm looking for that, what is digital twin? So I have a paper, but not on the digital twin itself, on the sensor modeling. I plan to write another paper, and hopefully I should do that early next year. I want to clarify what is a digital twin. It is. Okay. So case study number 3, that is the real-time leak detection. So this is also for oil and gas. So here we do the monitoring of the above ground pump station. So this is the not a buried pipeline, it's above ground. So this work is collaborate with a company called IntelliView. So that's in Calgary. So this company do the business for the monitoring. Let's say they use the surveillance camera to monitor the pump station. If there are any leak, they trigger the alarm, people will fix that. So this is their solution. They do the 24/7, let's say, around the clock around the monitoring, right? And but this is for the for they have the people engineer keep looking at the monitor, and if the trigger and they see, okay, this is the real leak or it's a false alarm, then they address this issue. So this is the bottom is their process they currently have for this. So our solution, so let's say there's a challenges for this inspection monitoring. So they use the thermal imaging. They use the visible, like say RGB camera for the monitoring, but there are challenges. So let's say if there are people, like say background information change, there are vehicle, there are bird, there are people coming to the picture, so they may trigger the alarm for that. So a lot of false alarm happen. Okay, and the small size, they cannot detect it. So you see, oh, this is a object detection problem. Yes, it's object detection, but the difficulty is, if you look at the literature, there are not many research or publication or literature about the object detection, especially for the fluid object detection. They have the small object detection. They have the different background object detection. But for the fluid, that is when I do the research before, when I write the proposal, there's only one research lab in the U.S. They do the water detection. Okay, because the shape it change, right? Shape it change. That that become the challenge for this issue. Okay, so here we think about the motion information. Okay, motion because the water is move. The other is the multimodal information, not only from the visible camera, also from the thermal imaging. So how we can use that for the detection. So before we doing this, similarly, we want to do the registration as you have two images on the left and right, but they are not aligned. The same pixel, the pixel do not associate with the same physical point of the target. So we want to do the registration first, right? So therefore, we have two work to do. So one is to registration. Here we propose a multi-object optimization-based registration approach. The other, we want to do the fusion about the detection. So we use the vision Fourier transform-based detection approach to do the detection. Okay, so this is basically the registration approach. This is also done by one of my PhD students. He's now in China working with the research institute, and some demo is available on GitHub. And this paper published on the information fusion. And yeah, so basically not only for this case, can be also used for other multimodal image registration. Okay, image registration. So this is a possible. This is a one word. So the other one is the detection from the IR, infrared or thermal image, and visible image. So basically, there are three key components here. For feature extraction, there's a ResNet, and the other is the vision Fourier transform and the feature pyramid network for detection. So then we can detect the item leak. Okay, so this is basically what we proposed. I think this work also published. Also published on IEEE transaction, and this is a later work, motion aware multimodal. This is a multimodal solution based on the motion. This is a multimodal with the motion and the multimodal things, right? But they use a different network and they do the detection. So this I think published on also information fusion journal, I believe. Yeah. So this is a detection results. So this is let's say we have our solution and we have the other available solution. Do some comparative study about this work. So from this work, I'm still thinking something. Lesson. Okay, so lesson we learned is when we do the leak detection. So leak is a process starting from the early stage to the final state, right? Let's say when you can detect it, that is the critical. Let's say when it starts, small leak, you can detect it, or it's already leaked for 12 hours, then you can detect it. That's maybe different. So in our study, I think we did not look into that. So we just say, okay, this is the leaked images, or this is a video. We can detect it. We use the matrix. We got the this value. So this is, but for industry, most important thing is when we can detect it, right? At the early stage, you don't want it be already leaked for 12 hours. Then you can detect it. It might be too late, right? Might be too late. So this work so delivered to the company, and the company got an award from the oil and gas industry in Houston, I think 2023. Okay. So the lesson we learned from this type of work, data fusion, that is beneficial, that is essential, very useful, but we must know when and how. Not necessarily anything you fuse that give you a better result. That's not necessary, because sometimes you fuse a bad information with good information that give you even worse results. So be very careful with that. And for data-driven approach, especially civil students now say, oh, we can use the deep learning, we can use the AI, we can use machine learning. You feel very excited about this work. But be very careful. Don't use the research approach by the computer science. This is, I realized this, I give a strong feeling about this. Because for computer science people, their attention, their focus is about the tool, right? So they say, oh, I got a 0.05% of improvement. My God, I got it published on they call the top conferences. But that number does not make sense to a civil engineer. So we must look at what is the most important, significant thing to a civil engineer. So as a civil engineer, civil researcher, you must know the story you have, rather than looking at the tool, happy with the tool only. Okay, that's very important. And the other is the last mile problem. Let's say you have different solution, how you can deploy it to the field, how people can use that, how you can maintain the tools in the field. That's the question. Okay, because right now, another machine learning for medical imaging analysis, right? A lot of publication, a lot of work, but the reality is none of them has led to significant of the clinical practice, which means useless. It's useless. Academia is useful, get a paper published, but in real life, there are a lot of issues when you use that. So similarly, when we look at this, we have to think about this. But if you're say, okay, I want to publish, I have a solution. The issue with the reviewers' mindset, they look at any innovation of your methodology, any improvement. They don't look at the significance of the problem you solve. So my suggestion, recommendation is when you write your paper, pay more attention, put more effort in the significance of the problem you have, how you solve the problem. That is more beneficial. The other thing is uncertainty and POD. So this is critical, but not fully explored yet, because a POD, that is expensive. Usually when we sell a NDT technique, we need to have a POD curve associated with that. So we look at the POD curve, we can compare this system is better than the other because of the POD. But when you come play with the model, with the AI come into the picture, where is the POD? Will the POD be consistent across different data set or different scenario or not? That's the question. Because the original POD that can different like a different data set, even though that has been could be obtained in the lab, but basically they give the information about the capability of the system for inspection, right? Okay, so this is the lesson we learned from the research perspective. The other is collaboration with the industry. That is very important because you got the you know the challenge, real life challenge, and domain knowledge, that is very important. And identify, start with high value problem. So from your domain knowledge and your expertise, you learn that. So digital twin, multiple sensing can be applied to different infrastructures like bridges, buildings, buried utilities, many other things. The same idea, same mindset could be applied to other things. Not only one individual sensing modality, you're looking at multiple modalities of that. So for the summary from the case study, I have one message. That is a digital transformation that is essential for the infrastructure applications, right? And the key enabler, multi-sensor data fusion, digital twin, that is a platform for information management and analysis, and continuous monitoring for the real-time intelligence, right? So this is the key enabler. Opportunity, okay? So infrastructure, now we looking for the life cycle management, life cycle, right? So for bridges, in China, we have a lot of new construction, new infrastructures. Now we're moving to the maintenance of this infrastructure. So that'll be another challenge coming. So that is, I know the civil is not that hot in China, because that is we already the peak for the construction. It's done, but we move to another peak for the maintenance, right? So and we need to leverage this methodology for different methodology to address the challenge from the condition assessment of infrastructure, especially for the smart city development and through the industry academia collaboration. Okay, so some acknowledgement, because I had this first talk at the City University of Hong Kong, so I appreciate thank for their professor and department and my collaborator and my students, and we got the support from Canadian funding agency, the NSERC and METEX. Okay. So that's all my talk. Any question, feel free, we can discuss. Thank you.
Is there any presentation? We still have time for the questions, the audience, and for also the online audience. If you have a question, you can pose it.
Okay, thank you so much.
So if I have any message here. Okay. So this year I have a new PhD student from this university, from the Transportation Institute, probably. He started his PhD in January. He got a CSC fellow scholarship, and I will ask him work on the pipeline with Rosen, because I have two PhD students graduate on the pipeline research. They are good. They publish a good paper, and they make a lot of great effort. But I still get the feeling they are still around, not into the center yet. So hopefully these students can move further about this research.
Actually, I have a question.
Yeah.
Thank you for your insightful presentation, Professor Liu.
Yeah.
I have a question about the data fusion process. As you mentioned in your presentation, data fusion is not always be better. So my question is, during the assessment of infrastructure during the process of infrastructure digitalization assessment, when is it advisable to use data fusion, and when it is not advisable?
Okay, so yeah, this is a good question. So as I mentioned, so basically we look at the size of the damage. So we first look at the individual technique for their individual. Let's say we use the UT to quantify the damage. We use FFL to quantify the damage, and we also group the damages into categorize the damage into different groups based on the size of that. So then we look at the performance for different groups. So we found that for the group of the small or large damage, maybe only individual technique can give you the good results. It does not has to do fusion. Fusion does not give you better results. So therefore, I think we must come up with some solution when we should do the fusion. Let's say could be set up a threshold. Let's say when the measurements go beyond that threshold, then we should do the fusion, something like that. But this is just the first observation from the data set we have. We have not come up with a general like a solution. Let's say in this case we should do this, in this case for that. There's a lot of research should be done for this. Yeah. Okay, thank you.
Other questions? If not, let's conclude this presentation. Thanks, Professor Liu, again for sharing his activities with us today. Thank you.
Okay.